Welcome back. Let's review rates of return and interest rate term structure. Alright, so in this video, we are going to be reviewing the fourth unit of financial mathematics, at least the way that I have broken up the topics. And the fourth unit is all about different rates of return and the interest rate term structure, which really just refers to spot rates and forward rates and a yield curve, but we'll talk about that more later. In particular, we're going to be reviewing the topics that I cover in lessons 25 through 30 of my FM video series. So that includes the internal rate of return, or IRR, the dollar-weighted rate of return, or DRR, the time-weighted rate of return, or TRR, inflation and real rates of interest, the portfolio method, and spot rates and forward rates. Now, if you were preparing to take the actuarial exam FM, there's actually a couple topics here that you don't need to worry about. You can ignore them because they're no longer tested on that exam. And that includes the dollar-weighted rate of return, the time-weighted rate of return, and the portfolio method. Those three topics or those three lessons you can ignore. You don't have to know them for the exam FM, but if you're just in some other financial mathematics course, it may be the case that you do need to know those topics, and so I've included them in this unit review video. Okay, I covered these concepts in my FM video series, so I want to make sure to review them, even though they're not tested on the exam FM anymore. Okay, now just like with my other unit review videos, the way that I've structured things here is we are first going to review all the different formulas you want to know for this unit, and then we'll move into our review problems. And so let's not waste any more time, and let's begin reviewing the formulas that you should know for Unit 4 on rates of return and the interest rate term structure. Alright, so first up we're going to be taking a look at the internal rate of return, or the IRR, and remember that the internal rate of return is the interest rate that satisfies the following equation. We have the sum of the present value of a set of cash flows, and we're setting it equal to 0. All right, that's all this represents right here. It's the net present value of a set of cash flows. You take the sum of your cash flows valued at time 0. Right, we have C sub k, which represents a cash flow at time t sub k, and we're multiplying it by a present value factor that takes it back that number of years or that number of periods to times 0, and we do that for all of the cash flows in a set of cash flows, add them together, and set it equal to 0. The interest rate that would be used in those present value factors that makes that equation true is the internal rate of return. Okay, so once again, I know the notation can be a little bit confusing, but this right here is just the net present value of a set of cash flows, where C sub k is the cash flow at the respective time t sub k, and n is the total number of cash flows that you're working with. All right, and remember, when you're setting up this type of equation to calculate an internal rate of return, there are two different cash flow types that you want to keep in mind. There are outflows and there are inflows. When we talk about outflows, we're talking about money that is being invested, money that you are losing, essentially, right? You're not gaining that money, you're spending it or investing it in something. And so we treat outflows as negative cash flows, okay? Those cash flows will be negative when we calculate the net present value. On the other hand, inflows refers to money being received. This is money that you get from your investments. All right, so it is money that is being gained. And we treat inflows as positive cash flows. Okay, so when you are setting up your net present value, inflows or money being received are positive cash flows. Now, finally, you'll see I have this little note down here, and it says, in most cases, only one internal rate of return will satisfy this equation. However, it is possible that sometimes more than one rate will satisfy the equation, and so in that case, one of two things will happen. Either it's going to be obvious which rate to use, meaning one will be non-negative, will have a positive interest rate as opposed to a negative interest rate. We typically don't work with negative interest rates. It's not out of the realm of possibility, but in most FM problems, you want to work with a positive interest rate. But the other thing that could happen is that a problem will specify what interest rate to use. It'll tell you something like the internal rate of return should be greater than 5% or something like that, right? So if you have two internal rates of return, and let's say both are positive, you have a 2% rate and a 7% rate, you would want to use the 7% rate because the problem told you it's going to be bigger than 5%. All right, so if there's more than one internal rate of return that satisfies this equation, either the problem needs to tell you which one to use, or one of them will be the obvious choice because it's a non-negative interest rate. Okay, but that's everything you need to know regarding the internal rate of return. So let's move on to our next formula. Now we're going to talk about the dollar-weighted rate of return, or DRR, and remember that the dollar-weighted rate of return is very similar to the internal rate of return, but it involves simple interest, and it only works with a 1-year period. Okay, more specifically, it satisfies the following equation right here, where you have the year-end balance of an account, you set that equal to the sum of the accumulation of the cash flows throughout the year for that account. All right, so it is a little bit different than the equation that we looked at for the internal rate of return because now we're working with accumulation factors, not present value factors. At least the way that I have this equation set up, it is possible that you could view it from a perspective where you would use present value factors, but I find it the easiest to look at the dollar-weighted rate of return from this angle, where you take the year-end balance and set it equal to the sum of the accumulation of the cash flows throughout the year. All right, and it's important to remember that that accumulation factor uses a simple interest accumulation factor, right? We have 1 plus a simple interest rate, which, by the way, is a dollar-weighted rate of return, and that's being multiplied by the time that the specific cash flow needs to be accumulated for. Now, it's important to remember that that amount of time, T sub k, is the time to the end of the year for that specific cash flow, C sub k, all right? And it's going to be measured in years. Typically, it will be measured as a fraction where you have the number of months left in the year divided by the total number of months in the year, which is 12. Okay, in dollar-weighted rate of return problems, you will most likely be working with different deposit and withdrawal amounts that take place at the beginning of certain months. So for example, it could be March 1st or April 1st or September 1st, something like that. And the number of months left in the year from that date would help you determine what this value of time is. Okay, so that about covers everything you need to know about this equation here, other than the fact that n, of course, is still the number of total cash flows you were working with in a particular scenario. Okay, the first cash flow will be the balance at the beginning of the year for the account, and then every cash flow after that will be either a deposit or withdrawal that you need to accumulate using a simple interest accumulation factor where the interest rate is the dollar-weighted rate of return. It's the interest rate that satisfies this equation. Okay, but that's it for the dollar-weighted rate of return. Next up, let's take a look at the time-weighted rate of return, or TRR, and the time-weighted rate of return measures growth in an account or fund for a 1-year period, very similar to a dollar-weighted rate of return, except that growth is measured by compounding returns over successive parts of the year. All right, and the formula looks a little bit complicated at first, but remember, in time-weighted rate of return problems, you will be given information very similar to what you would be given in a dollar-weighted rate of return problem. You'll be given the balance of an account at different months of the year, as well as deposits and withdrawals that take place at different months throughout the year. And so you should have a list of account balances to work with that we represent with F sub k. These are different fund balances at different times before any deposits or withdrawals are made. I typically like to refer to those as reported balances. They are balances that are reported at different times throughout the year. And so the way you calculate the time-weighted rate of return is you take the first reported balance, which is the first reported amount after the initial balance, which we represent with A. So A is the initial balance of the account at the beginning of the year. You take the first reported balance divided by that initial balance, and then you multiply by the next reported balance divided by the previous reported balance plus any cash flows, meaning deposits or withdrawals, at that time. Notice that the times here match up. We have F sub 1 plus C sub 1. So you add or subtract any deposits or withdrawals at the time of that reported balance, and that's what's in the denominator of this fraction. But then you multiply by the next reported balance and divide by the previous reported balance plus or minus any cash flows at that time. And this pattern continues up until you get to your last reported balance, which I represent with F sub k, and you divide by the previous reported balance plus any cash flows at that time, and then you multiply by the final balance of the account and divide it by that previous reported balance, which was the last reported balance plus or minus any cash flows at that time. And then after you do that, you subtract 1. And it's important to remember that you are subtracting 1 from all of this, right? You want to multiply all of these fractions together, then subtract 1. You don't just subtract 1 from the last fraction, you subtract it from all of these fractions multiplied together. Okay, it looks like a complicated calculation at first, but if you've watched my lesson and examples video on the time-weighted rate of return, then you probably know that this is not as complicated of a calculation as it initially seems based purely on the formula. Okay, it can be a little overwhelming at first, but once you see the calculation in an example problem, it's not too bad. And of course, we will review that calculation later on in this video with a review problem. But that's it for the time-weighted rate of return. Let's move on to our next formula. Now we're going to look at the formulas for inflation and real rates of interest. Remember that you can find the real rate of interest for a particular scenario by taking the current interest rate, subtracting the inflation rate, and dividing it by 1 plus the inflation rate. All right, so the real interest rate is equal to I minus R divided by 1 plus R. Or an alternative way of calculating a real rate of interest, if you were given the right information, is to take the value of the amount of real return and divide it by the value of the amount invested. All right, so really what's going on here is in the numerator, you have your increase or decrease in purchasing power due to the inflation rate and divide it by the amount of your original investment where you take inflation into account. All right, in terms of the math, these two equations are the same, but this is probably the one that you are going to use the most often because it is a simpler version of this formula. All right, if you're given the proper information, you know your current interest rate, you know the inflation rate, this formula is what you will use, and it's pretty straightforward. Okay, and that's really it for inflation and real rates of interest. Next up, let's talk about the portfolio method, which just like the dollar-weighted rate of return and time-weighted rate of return, this is a topic that if you were preparing to take the actuarial exam FM, you can sort of ignore this part. This is not going to be tested on that exam, but it doesn't hurt to learn about the formula regardless, or how to use the portfolio method, because it's really not too complicated. In general, remember that the portfolio method uses a set of what we call portfolio rates, where each portfolio rate corresponds to a particular year. And we represent those portfolio rates with I and a superscript of Y, where Y is the year for that portfolio rate. And so typically what we do with these portfolio rates is we accumulate an investment over time where each of those portfolio rates is only used for 1 year, right? So if we want to accumulate an investment from year Y to a T number of years in the future. So for example, if Y is 2020 and we want to accumulate an investment for 4 years, that would take us to 2024. The accumulation at time 2024 would be equal to our initial investment X at time Y multiplied by accumulation factors using the respective portfolio rates. You would use the portfolio rate for the first year, and then the portfolio rate for the next year, and the next year, and the next year, until you get to the last portfolio rate for the year that would take you to your final year. So in our case of accumulating to 2024, we would have a portfolio rate for 2020, then 2021, then 2022, then 2023, because then we will have accumulated to 2024. Okay, we don't use the portfolio rate for 2024 because we are stopping at 2024. That's why the last portfolio rate is Y plus T minus 1. The last one that you use for an accumulation is the portfolio rate for the previous year, the year before the year that you want to accumulate to. Okay, I hope that makes sense. If not, you'll see what I'm talking about when we get to our review problem on the portfolio method. And so now we're ready to move on to our last set of formulas for Unit 4. Let's take a look. Our last set of formulas all have to deal with spot rates and forward rates. And the wording and notation surrounding spot rates and forward rates can be a little bit confusing because there's not one single agreed upon notation for spot rates and forward rates. But I'm going to try to do my best here to clear up any confusion surrounding that. To start, let's talk about forward rates. The most common way that I see forward rates referred to is with this wording. You have the N-1 year forward rate. What that means is you have a forward rate between years N-1 and N. So if this was a 3-year forward rate, we're talking about the forward rate from year 3 to year 4. All right, and to calculate that forward rate, you would take an accumulation factor for the spot rate at the later year, which in our example would be the spot rate for year 4. So that would be S sub 4. You'd take 1 plus that spot rate to the power of 4, and you would divide it by the accumulation factor for the spot rate for the previous year, which in our example would be S sub 3, the spot rate for a 3-year term. So you would have 1 plus S sub 3 to the power of 3, and then you would subtract 1 from this fraction, and that would get you your respective forward rate. Now, another way that you might see forward rates referred to is with this wording. You might have an N-year forward rate deferred M years. Sometimes that is associated with this notation, which is a little bit different than what I have right here. Instead of having lowercase f with a subscript of the 2 years that the forward rate takes place between, with a comma separating them, we have this subscript of n before f and then the subscript of m after, where n is the number of years that the forward rate takes place for and m is where it starts. All right, so when it says an n-year forward rate deferred m years, it's saying that the forward rate takes place for an n number of years and it starts at year m. Okay, so if this said a 1-year forward rate deferred 3 years, for one thing, you would have 1 and then f and then 3, but really if you were going to use this notation, which is what I prefer to use, then you would be looking at the forward rate f sub 3 comma 4, right? You would have 3 and then 1 plus 3, which is 4. So that would be the 3-year forward rate from before, if that makes sense. Okay, it can be tricky to understand the wording for forward rates, but these are really the two most common ways that you will see them referred to. I will show you a timeline in just a second to sort of jog your memory on what forward rates and spot rates are, but before we do, real quick, a forward rate from year 0 to year 1, or a 1-year forward rate deferred 0 years, that is the same as the spot rate for a 1-year term, or S sub 1. Okay, so just keep that in mind. This forward rate is equal to this spot rate. Now, just to remind you of how spot rates and forward rates work and this whole idea of an interest rate term structure, let's quickly take a look at a timeline here. Remember that when you use spot rates, you are looking at interest rates that accumulate interest for certain term lengths starting from today, time equals 0. So S sub 1 is a spot rate for a 1-year term length. S sub 2 is a spot rate for a 2-year term length. And S sub 3 is a spot rate for a 3-year term length. Notice that they all start at time 0 or today. Now, forward rates, on the other hand, forward rates deal with terms that do not start today at time 0, but take place between other periods of time and for different term lengths. So, for example, right here, we have a forward rate from year 1 to year 2, or another way that might be referred to is a 1-year forward rate deferred 1 year. That is a forward rate that you would use for an investment with a term length of 1 year starting at time 1. I've tried to include both notations that I showed you earlier for each forward rate on this timeline. Just note that I will most likely only use this notation in actual review problems, but these other notations are valid as well. I just typically don't use them. But anyway, a forward rate from year 2 to year 3, or a 2-year forward rate, or another way that that might be referred to is a 1-year forward rate deferred 2 years. That is a forward rate that takes place between year 2 and year 3 that you could use on an investment that you want to measure growth on for a 1-year term starting at year 2. Or you could also have a forward rate that takes place for a gap larger than 1 year, such as 2 years. We didn't look at that formula yet. We'll look at it in a second. The formula that we already looked at was for a forward rate that only spans a 1-year gap, right, from year 3 to year 4, or from year 4 to year 5, something like that. This right here is a forward rate that spans 2 years. Specifically, it's the forward rate from year 1 to year 3, which could be referred to as a 2-year forward rate deferred 1 year. It starts at year 1 and spans a 2-year period. That is another type of forward rate that you could work with, and that's how it would look on a timeline. Okay, I hope these timelines were helpful in jogging your memory on how spot rates and forward rates work. Remember that all spot rates start at time zero and forward rates kind of fill in the gaps. They work for terms of various lengths, but they don't start at time zero. They start at some other moment in time. All right, but as promised, let's take a look at the formula for a forward rate that spans a gap larger than 1 year. In most cases, forward rates that you work with will only span 1 year, but it's not out of the realm of possibility that you will need to work with a forward rate that does span a gap larger than 1 year. If that's the case, this is the formula you want to work with. For a forward rate from year K to year N, you want to take the accumulation factor for the spot rate associated with the later year. So you'll have 1 plus S sub n to the power of n, and you'll set that equal to the accumulation factor for the spot rate that corresponds to the earlier year, and then multiply that by an accumulation factor for the forward rate, where the power is the later year minus the earlier year. And to sort of help you visualize where this formula comes from, you can take a look at this timeline right here. This is the forward rate we're trying to find. It spans a period from year K to year N, where this period of time is larger than 1 year, of course. What this equation is saying is that if you use a spot rate S sub n, which would accumulate an investment from time 0 to time n, that would be the same as using S sub k for this period of time, and then this forward rate for the rest of that time, for those n minus k years. Okay, so using these two interest rates, this spot rate and this forward rate, from year 0 to year n should accumulate the same amount of interest as this spot rate S sub n would. Okay, so that's sort of the visualization of this formula, if that helps you make sense of what it's doing and why it is the way that it is. But that's pretty much it. That's everything you need to know regarding formulas for spot rates and forward rates. And this was also the final formula that I wanted to review for Unit 4 of Financial Mathematics on rates of return and the interest rate term structure. Okay, and so now we are ready to move into our review problems. Let's take a look at our first one. Okay, so here's our first review problem. Before we get started here, I just want to say this is a review video, so if you want to challenge yourself and see how well you know these different concepts in Unit 4, I would highly encourage you to pause this video as soon as a new problem shows up on the screen and try it out for yourself first, see how well you do, see what kind of answer you get, and then play the video and compare your work to my work or your method of solving to my method of solving. It's very possible that you might solve the problem differently than me and still get the right answer. That's totally fine. That's one of the great things about math, is that oftentimes there are multiple ways to get to the right answer, and as long as your way of finding it makes sense to you and it's accurate, it makes sense to do it that way, then that's fine. Okay, now you don't have to use this video that way. You can just watch me solve the problems. That's fine. But I would recommend that you try to take the time to solve these problems for yourself first, and then compare your work to my work. All right, but enough about that. Let's work on our first review problem here. We have Aaron invests $200,000. This investment returns $50,000 immediately, $100,000 in 6 years, and $120,000 in 12 years. What is Aaron's internal rate of return? Okay, so hopefully it's pretty obvious based on that last sentence that we are working with an internal rate of return in this problem. We want to calculate an internal rate of return, and to do that, we've been given a set of cash flows. And so what we will have to do is set up an equation where we calculate the net present value of the cash flows and set it equal to 0. And to help us do that, I think it's a good idea to draw a timeline to really get an idea of where these different cash flows are valued so that we can set up that net present value calculation accurately. So I'm going to draw a timeline here. Our last cash flow takes place 12 years in the future. So we're going to include a total of 12 years here. This will be time equals 0, and this will be time equals 12. And then in the middle there, we have time equals 6. And then in between there, we have time 1, 2, 3, 4, 5, and then 7, 8, 9, 10, 11. Now, we're told that Aaron invests $200,000, so that's talking about what he's investing today, and an investment is an outflow, right? That is money that Aaron is essentially losing, right? He's spending it. He doesn't have that $200,000 anymore. He's investing it. So at time 0, we have a cash flow of negative $200,000. Then after that, we're told that his investment returns $50,000 immediately. So what that tells us is that at time zero, he immediately gets back $50,000. He has an inflow of $50,000. So that's a positive cash flow of $50,000. And then we're told that he receives $100,000 in 6 years. So at time 6, we have another inflow or positive cash flow of $100,000. So we have plus 100,000. And then finally, in 12 years, we have another inflow or a positive cash flow of $120,000 that Aaron receives as a return on his original investment. Okay, so at time 12, we have plus 120,000. All right, so these are the cash flows that we are working with in this scenario. So now what we want to do is set up an equation where we set 0 equal to the net present value, where we value all of these cash flows at time 0. All right, so let's do that. We're going to set 0 equal to the present value of all these cash flows. The first two right here are already valued at time 0, where the present value would be valued. So we can just write in minus 200,000 plus 50,000. And then we want to add that to these two cash flows valued at time 0. So we're going to have $100,000 that needs to be brought back 1, 2, 3, 4, 5, 6 years. So we have 100,000 times a present value factor to the power of 6. And then for the $120,000, that needs to be brought back 12 years, right? It's currently valued at time 12, but it needs to be valued at time 0, so we need to bring it back 12 years, and we do that by multiplying by a present value factor to the power of 12. So we'll have plus 120,000 times v to the power of 12. Okay, so that's the setup, but we can simplify it a little bit. We have two like terms, or two constant terms that can be combined to be one term. Negative 200,000 and positive 50,000 can be combined to be negative 150,000. So we'll have 0 is equal to negative 150,000 plus 100,000 times v to the power of 6 plus 120,000 times v to the power of 12. Now at this point, what do we need to do? Where do we go from here? Well, we have to find Aaron's internal rate of return. And the internal rate of return is the interest rate that satisfies this equation, that makes this equation true. In particular, we're talking about the interest rate that would be contained within these present value factors. But how would we solve for that? It seems like it's going to be pretty complicated at this point in time, right? We have a present value factor to the power of 6 and another present value factor to the power of 12. That seems kind of tricky. How are we going to solve for that interest rate? Well, you have a couple different options. If you are familiar with a financial calculator, this is actually a pretty simple calculation that you could do. You could just enter these cash flows into the cash flow feature of the financial calculator. And I'll show you how to do that at the very end of this example problem. What I want to do first is actually show you how you could calculate the internal rate of return by hand, because there are also scenarios where you will need to use algebra and a calculator won't be able to help you. So it's good to also see the algebra skills involved in solving some of these problems. And so what we're going to do here is actually notice that we have a quadratic expression here. It's hidden, but it is there. Here's what I'm talking about. Watch what happens in this equation if I let a new variable x equal a present value factor to the power of 6. Watch what happens if we do that. Our equation will become 0 equals negative 150,000 plus 100,000 times x, and then we'll have plus 120,000 times x squared, right? We have v to the power of 12 right here. Another way that that could be written is v to the power of 6 squared, right? When you have a value raised to an exponent, the way you simplify this is by multiplying the exponents. So 6 times 2 is 12. This is true. So if we let x equal v to the power of 6, then we have x squared, which is what I wrote right here. So that checks out. But now notice what we have here. It's a quadratic expression that we could solve by either factoring or using the quadratic formula. And to make that a little bit easier on ourselves, notice that we could reduce each of these terms by a factor of 100,000. If we do that, our equation will become a lot simpler to work with. we'll have 0 equals, and I'm going to change the order. So our x squared term is first, and then we'll have the x term, and then we'll have the constant term. But if you divide each of them by 100,000, you'll have 1.2 times x squared plus x, because 100,000 divided by 100,000 is just 1, and then you'll have minus 1.5. Okay, and now we have a quadratic expression that we could solve by either factoring or using the quadratic formula. And in this case, I'm going to choose to use the quadratic formula since we're working with decimal values. That doesn't seem like a lot of fun to try and factor. So remember for the quadratic formula that the coefficient of the x squared term is a, the coefficient of the middle term is b, and then the constant term is c. And the quadratic formula says that x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. All right, so in this case, x is equal to negative 1 plus or minus the square root of 1 squared minus 4 times 1.2 times 1.5 divided by 2 times 1.2. And so if you were to calculate both of these answers, one of them is where you add the square root, and the other one is where you subtract the square root, you should find this. You'll get that x is equal to 0.776 and some more decimals, and x is equal to negative 1.6098 and some more decimals. But now remember what we set x equal to. X is equal to a present value factor to the power of 6. So really, we have v to the power of 6 is equal to 0.776 and some more decimals, and v to the power of 6 is equal to negative 1.6098 and some more decimals. And now we can solve for our internal rate of return, the interest rate associated with this present value factor. And if we do that, the first thing I would do is take the reciprocal of both sides of the equation, flip the numerator and denominator. So the present value factors become accumulation factors. And then on the other side of the equation, we just take 1 divided by those respective values. So you'd have 1 plus I, which is the internal rate of return, to the power of 6 is equal to 1 divided by this value, which will be about 1.28. And then we'll have 1 plus I to the power of 6 is equal to negative 0.62118 and some more decimals. That's 1 divided by this number. Now, notice that for this equation, we're saying that this accumulation factor is going to produce a negative result, and that's most likely not what we're looking for here. The problem doesn't really tell us, but since it doesn't tell us, we're assuming that the internal rate of return that we want here is going to be an interest rate that causes positive accumulation, not a negative accumulation. All right, so at this point, we can rule out this one. That's not what we want. So if you solve for the interest rate in this equation by taking the 6th root of both sides of the equation, that gets rid of this power of 6, and then subtracting 1, you should find that the internal rate of return is equal to 0.043 or 4.3%. Okay, that's the final answer to this problem. At least that's how you could find this answer by hand. Now, it might actually be quicker to use a financial calculator, as I sort of alluded to earlier. So let me actually show you how you do that real quick. Because if you were working with more cash flows than we're working with in this specific review problem, using a financial calculator would basically be necessary in order to find the internal rate of return. So let's do this in the calculator real quick. If you have your financial calculator here, what you want to do is go to the cash flow menu by hitting the CF button, and then clear that out if there's anything in there. So I'm going to hit second clear work. And for CFO, that's where we put our cash flow at time 0, which in this case would be our negative $150,000. So I'll put 150,000, make it negative, and hit enter, then go down. Our cash flow at time 1 is nothing, right? We have a cash flow at time 6 and a cash flow at time 12. So this gets a little bit tricky here. You just want to hit enter and make sure that the cash flow at time 1 is 0, and you only want to put in cash flows for time 6 and time 12. So I'm going to go down. Whenever you see F01 or F0 any number, that's just talking about the frequency of that cash flow. So if it's not more than 1, which in most cases it won't be, you can just leave that alone. So I'm going to go down. Cash flow 2 is 0, then cash flow 3 is 0, cash flow 4 is 0, Cash flow 5 is 0. Now we're at cash flow 6, where we have $100,000. So we'll do 100,000, and that's positive, so we'll enter that in. The frequency is 1, so we're good there. Let's go down to 7, 8, oops, sorry, there we go. There's 8, then 9, 10, 11, all right, 12. This is not 0. It's $120,000. So we have 120. And then you want to hit enter. And now all of our cash flows have been entered in. So what we can do is hit the internal rate of return button and then hit compute. And you might have to wait a little bit. Sometimes this takes a while. But there we go. There's the 4.3% internal rate of return that we calculated by hand, but now you can see you can also find using the financial calculator. All right, so if you've never seen that before, that's how that works. That's how you can do that. If you want to save yourself some time, that's probably going to be quicker in most cases than using the quadratic formula. Okay, but that's it for this example. Aaron's internal rate of return is 0.043 or 4.3%, and so we have completed our first review problem. Let's take a look at the next one. For our second review problem, we have Ronald's savings account earns an effective rate of I equals 0.13, on which 45% income tax is paid. Given that the inflation rate is 10% each year, what is Ronald's annual after-tax real rate of return? Okay, so if you want to take a moment and pause the video, try this problem out for yourself, see how you do, and then once you're ready to check your work, feel free to play the video and see how I solve it. Now, to start, I think it should be clear from this problem that we are working with an inflation rate and calculating a real rate of interest, or a real rate of return, right? We are explicitly told that the inflation rate is 10%, and we want to know Ronald's annual after-tax real rate of return. Now, this problem isn't as simple as using the formula that I real is equal to the current interest rate minus the inflation rate divided by 1 plus the inflation rate. All right, it's not going to be quite this simple, at least not immediately, because yes, Ronald's account earns an effective rate of I equals 0.13 and the inflation rate is 10% or 0.1, but we're given this other little piece of information that changes the problem slightly. We are told that Ronald pays 45% income tax on what he earns from his account. And we're not just looking for any old real rate of return, we're looking for the after-tax real rate of return. In other words, what is his actual return rate considering the inflation rate and the fact that 45% of his income is going to disappear thanks to income tax. All right, so what we have to do here is take that into account. We have to consider the effects of the fact that he pays 45% income tax and what that means for his effective rate of interest. All right, and so here's how I'm going to label that. The before tax interest rate that we've been given is 0.13 or 13%. And so his before tax interest rate is equal to 0.13. The question is, what is his after tax interest rate, right? What is that equal to? Because that's going to be the actual current interest rate that we use in this equation, right? That's what this I will be. It's not going to be 13% or 0.13, which is the before tax current interest rate. It's going to be the current after tax rate because we want the after tax real rate of return. So the current interest rate that we use should also be the after tax interest rate. Okay, now how do we actually go about finding that rate, right? How do we find the after tax interest rate for Ronald's account? Well, we have to think about what it means for Ronald's savings account to pay 45% income tax. And essentially what that's going to mean for us in terms of our calculations is that even though his account is earning a 13% interest rate, really he's earning less than that since 45% of it is going to be used for paying off his income tax, right? He doesn't actually get to keep 45% of the money that he earns in that account for the year. So what we have to do is take that 13% interest rate and remove 45% of it. Now, that's not as simple as subtracting 0.45. That's not what I mean. What I mean is this 13% interest rate represents 100% of the interest that Ronald would earn in a year, but we want to remove 45% of it So what we would do is multiply that interest rate by 1 minus 0.45, right? That is the income rate percentage, but expressed as a decimal. And essentially what we're calculating here, if you were to distribute 0.13 through this quantity, you would be taking that 13% interest rate and subtracting 45% of it, because you're taking 0.13 times 0.45, right? That's what's actually going on there. We're removing 45% of that interest rate to account for the fact that 45% of it is paid towards income tax. All right, so if you do this calculation, it actually turns out to be 0.13 times 0.55, because 1 minus 0.45 is 0.55. And if you multiply these two numbers together, you will get an after-tax rate of 0.0715. All right, that is the current after-tax interest rate for Ronald's savings account. Okay, he earns 13% every year, but 45% of it is going to income tax, so he really only earns 0.0715 or 7.15% interest. That's his current after-tax interest rate. So that's the interest rate we're going to use in this calculation, which now we can do. It's a pretty straightforward calculation from this point forward. We know that the inflation rate is 10% each year, which as a decimal, that means R equals 0.1. So here's our calculation. The real rate of return, or more specifically, Ronald's after-tax real rate of return, will look like this. We have that current after-tax return rate, which is 0.0715. We subtract the inflation rate, which is 0.1, and we divide by 1 plus the inflation rate, which is still 0.1. Okay, now simplifying, this will be equal to negative 0.0285 divided by 1.1. And if you plug that in your calculator, you will find that the after-tax real rate of return is negative 0.0259, and some more decimals, or negative 2.59%. That is the after-tax real rate of interest. Okay, so that would be the final answer to this problem. Notice that that real rate of return is negative, which is not a good thing for Ronald. That means that the purchasing power of his savings account is decreasing every year, which just goes to show the negative effects of a 10% inflation rate each year. That's kind of ridiculous, and so you would probably expect Ronald's purchasing power to decrease. Okay, and so that's it for our second review problem. Let's move on to the next one. For our third review problem, we have a fund uses the portfolio method with the annual rates given in the table below. If $2,500 is invested in the fund on January 1st, 2025, what will be the balance on January 1st, 2028? How much should be deposited on January 1st, 2024 to accumulate that same balance by January 2029? Okay, so this problem has two parts to it. There's two different questions, and so we're going to focus on one at a time. I'm going to start with the first question, and then we'll talk about the second question after we finish the first one. Okay, because the second one relies on us getting the answer to the first part. Now, if you want to take a moment to pause the video and try this problem out for yourself, now's the time to do that. But once you're ready to compare your work to my work, then play the video again, because now I'm going to work through the solution. The first thing I want to point out about this problem is that we are very clearly working with the portfolio method. The problem tells us that within the first few words, right, a fund uses the portfolio method with the rates given in the table below. And you can see that we have a list of portfolio rates that correspond to different years. We have 2024, 2025, 2026, 2027, and 2028 with their respective portfolio rates. Now, in particular, we want to use these portfolio rates to determine the balance on January 1st, 2028 of $2,500 if it's invested in the fund on January 1st of 2025. Okay, so our initial deposit that I like to label with X is equal to $2,500. It's invested in the fund on January 1st, 2025. We want to know its balance 3 years later on January 1st, 2028. And so here's what's going on in this problem. If I draw a small little timeline here, this is January 1st of 2025. This will be January 1st of 2026. This is January 1st of 2027. And this is January 1st of 2028. This is where our deposit was made. We need to accumulate interest on this initial investment for each of these 3 years, from 2025 to 2026, from 2026 to 2027, and from 2027 to 2028. And so we need to choose the appropriate portfolio rates for each of those years when we do this accumulation calculation. All right, for this first period, this would be all of 2025, right? This is from the beginning of 2025 to the beginning of 2026. So this period right here is 2025. We would be using this portfolio rate for 2025, right? So for this period, we're working with 8.13%. Then for 2026, we're going to be using this portfolio rate of 10.05%. So that will be for that year. And then for 2027, which would be this period, we are working with this portfolio rate of 6.59%. So I'll put that in the timeline as well. Okay, so those are the 3 interest rates, or the 3 portfolio rates that we're going to work with here. And so let's accumulate this $2,500 investment to the beginning of 2028. The value in 2028 will be $2,500 times 1.0813, right? That is 1 plus this portfolio rate, but as a decimal, of course. 8.13% is the same as 0.0813. Then we're going to multiply it by the accumulation factor using this portfolio rate for the next year. So we have 1.1005. And then we'll multiply by an accumulation factor for this portfolio rate. And so we'll have 1 plus that rate, but as a decimal. So we have 1.0659. Okay? And that's really it. This is our entire setup for this calculation for the first part of this problem. So if you plug this into your calculator, if you do all this multiplication, you will find that at the end of 2028, that $2,500 will become $3,170.97. That is the answer to the first part of this problem. That is the balance on January 1st, 2028 of that $2,500 invested in the fund on January 1st of 2025. But now what about our second question? It says how much should be deposited on January 1st, 2024 to accumulate that same balance by January of 2029? Or in other words, how much should be deposited at the beginning of 2024 to accumulate this same amount of $3,170.97 by January of 2029. And I made a slight typo here. That should say January 1st of 2029, just like all the other dates. But regardless, hopefully it was obvious that we're talking about the beginning of January for all of these years. So we are talking about January 1st of 2029. Okay, but back to the question. We know that $2,500 in 3 years, starting at 2025, gets us this amount. We want to know how much to deposit at the beginning of 2024 to get this same amount over a longer period of time, from 2024 to 2029, which is a 5-year period. And so in this case, it looks like we're going to be working with all of these portfolio rates that we've been given. Okay, we're going to need to use this 7.25% interest rate for all of 2024, and we're going to need to use this 7.93% interest rate for all of 2028, which, combined with all the other portfolio rates, will take us to January 1st of 2029. All right, so here's our setup. We want to accumulate $3,170.97, which, by the way, that is rounded off to 2 decimal places. You might want to include more decimals in that value when you use it later to solve for our initial investment amount, because we're going to be setting that equal to the initial investment, X, but then we need to accumulate that initial investment for 5 years using all these portfolio rates. Okay, and here's what that will look like. We'll have 1.0725, and then we'll multiply by 1.0813, then we'll multiply by 1.1005, then we'll multiply by 1.0659, and finally we will multiply by 1.0793. Okay, this is the accumulation factor for 1 year using this portfolio rate. This is the accumulation factor using this portfolio rate. This is the accumulation factor for this portfolio rate. This is the accumulation factor for this portfolio rate, and this is the accumulation factor for this portfolio rate. Each of them are only used for 1 year because they correspond to 1 year. Okay? So if you multiply all of these values together, what you'll have is 3,170.97 is equal to X, multiplied by about 1.468 and some more decimals, and then dividing both sides by that number will give you the final answer that initial deposit, which I'm going to use a different color here just so we don't get it confused with this initial deposit. The initial deposit that you would want to make at the beginning of 2024 should be $2,159.74. Of course, that is rounded off to 2 decimal places. All right, but that is the final answer to the second part of this problem. If you deposit this much at the beginning of 2024, you will have $3,170.97 by the end of 2028 or the beginning of January 2029. Okay, and so with that is it for our third review problem. Let's move on to the next one. Hey there, real quick, before we move on to the next part of this video, if you are currently studying financial mathematics with the intent on taking the exam FM, then I want to give you a gift for watching this video today. I want to give you my free 6-week studying strategy guide for exam FM. Inside the PDF file, I lay out a reasonable studying timeline that you can follow to prepare for the exam FM in just 6 weeks using my own content as well as some other resources online. By all means, it is not the only way to prepare for the exam, but it can certainly help you get started. So if you're struggling to stay organized in your studying of FM topics or want an easy to follow schedule for preparing for your exam, then this guide is for you. And it's absolutely free. Just head on over to jkmathematics.com/studyfm 6 weeks. Once again, that's jkmathematics.com/studyfm 6 weeks. Or you can find the link in the description. Okay, now back to the video. For our fourth review problem, we have Mia's investment account activity for 2023 is summarized by the table below. Determine Mia's dollar-weighted rate of return and time-weighted rate of return. Okay, so if you're preparing for the actuarial exam FM, you might want to skip this problem. You're not going to be tested on the dollar-weighted rate of return or the time-weighted rate of return, at least not at the time that I'm recording this video. Those are no longer tested on that exam. However, if you do need to know these two types of rates, then this is going to be a good practice problem because you're given a big table of account activity for a 1-year period, and you need to determine how to use that information to calculate both of these different rates because they both use the same type of information. It's just that the calculation is slightly different. So if you want to take a moment to pause the video and try this problem out for yourself, now's a good time to do that. See if you can calculate each of these rates of return. And then once you're ready to see the answers or the solutions, feel free to play the video and watch me work through finding these two rates of return. Okay, the first thing I'm going to do here is just simply read through this table to make sure that we are all on the same page. On January 1st, the account's balance is $1,000, and that is the balance before any deposits or withdrawals. That is going to be the case for all of these balances. Of course, at the beginning of the year, there are no deposits or withdrawals. Usually that's the case. You're not going to have any deposits or withdrawals at the beginning or the end for one of these tables. The beginning and the end are usually just your beginning balance and your ending balance for the year. But then on March 1st, we have a balance of $1,150 and a deposit of $200. On May 1st, we have a balance of $1,400 and a withdrawal of $250. On August 1st, we have a balance of $1,200 and a deposit of $360. Then on October 1st, we have a balance of $1,700 and a withdrawal of $100. Okay, and finally, our ending balance on December 31st of this year, in this case 2023, we have $1,500. Okay, so what I always recommend you do for a problem like this where you're calculating a dollar-weighted rate of return or a time-weighted rate of return, in this case we're doing both, so this is really going to be helpful, and that is to draw the timeline. So here's my timeline. This right here will be the beginning of the year, which is January 1st, and this right here will be the end of the year, which is December 31st. Then in between there, we have 4 dates to account for. We have March 1st, May 1st, August 1st, and October 1st. Now on January 1st, the fund balance is $1,000, so we have $1,000. Then on March 1st, the balance is $1,150. On May 1st, it's $1,400. On August 1st, it's $1,200. On October 1st, it's $1,700. And then at the end of the year, it's $1,500. Now for our deposits and withdrawals, we have a deposit of $200 on March 1st. So I'll write that like this. We have plus 200. On May 1st, we have a withdrawal of 250, so we have minus 250. Then on August 1st, we have a deposit of 360, so we have plus 360. And then on October 1st, we have a withdrawal of 100. So I'll write minus 100. This is typically how I like to write out that information given in these tables for these types of problems involving a dollar-weighted and time-weighted rate of return, because it makes it really easy for us to set up the equations to calculate each of these rates. And let's start with the dollar-weighted rate of return. Let's find that first. For the dollar-weighted rate of return, what we do is we take the end balance and we set it equal to all of the cash flows made throughout the year, as well as the initial account balance accumulated to the end of the year. All right, so here's what that looks like. We'll have 1,500 is equal to the initial account balance of $1,000, but accumulated for the whole year using simple interest, right? Remember that a dollar-weighted rate of return works with simple interest. So we're multiplying by 1 plus that dollar-weighted rate of return, which I'll represent with I, and that's going to be multiplied by the amount of time that this account balance needs to be accumulated for, which in this case is an entire year. And that value of time is always measured in years, so we would just be multiplying by 1, but we don't really need to write that. So I'm just going to simplify this by just writing 1 plus I, okay? Anything times 1 is just itself. It's unnecessary for us to write that out. Now, let's take care of the different cash flows. And what I mean by that is the deposits and withdrawals. For a dollar-weighted rate of return, we don't care about any reported balances throughout the year. We only care about the beginning and the end balance in this case. Okay, so let's just focus on the deposits and the withdrawals. First up, we have plus 200, and that's made on March 1st. So including March, how many months are left in the year? Well, you'd have a total of 10 months because only January and February have been completed, so there's 10 months left in the year. So in this case, we have 1 plus the dollar-weighted rate of return times 10 months out of 12 months of the year. Okay, that's how you write out that value of time for our simple interest accumulation factor. You multiply I by the amount of time in years that you need to accumulate the cash flow for. In this case, it's a fractional amount of a year, in particular 10 months out of the total of 12 months in the year. Okay, now let's move on to our next cash flow, which is a withdrawal of $250. So we have minus 250, and then that was made on May 1st. So including May, there are 8 months left in the year that we need to accumulate that for. So we have 1 plus I times 8 divided by 12. Then we have a deposit of $360 on August 1st. So we'll have plus 360 times 1 plus I times the number of months left in the year that you need to accumulate that deposit for, which including August is 5 months. So we have 5 divided by 12. And then finally, we have this withdrawal of $100 to account for. So we have minus 100 times 1 plus the dollar-weighted rate of return multiplied by the number of months remaining in the year, divided by the total number of months, of course. And in this case, that withdrawal was made on October 1st. So including October, there's 3 months left in the year. So we have 3 divided by 12. Okay, so now all we have to do to calculate the dollar-weighted rate of return is to simplify this expression, for one thing, and then we need to solve for that dollar-weighted rate of return, which is I. Okay, so let's do that. The first thing I'm going to do is distribute this $1,000 through this quantity. So we're going to have 1,500 is equal to 1,000 plus 1,000 times I. Then I'm going to simplify these fractions here. 10/12 is the same as 5/6. So if we multiply 200 through this quantity, we'll have plus 200 plus 200 times I times 5/6. Then if we distribute negative 250 through this quantity, we'll multiply it by both of those terms, and 8 divided by 12 reduces to 2/3. So we have minus 250 and then minus 250 times I times 2/3. Then we'll distribute 360 through this quantity. 5/12 can't really be reduced, so we're just going to have plus 360 and then plus 360 times I times 5/12. And then finally, we want to multiply negative 100 by both of the terms in this quantity. And of course, 3/12 simplifies nicely to 1/4. So we'd have negative 100 times I times 1/4, and 1/4 of 100 is 25. So we have minus 100 minus 25I. Okay, hopefully you were able to follow that little bit of mental math. Now what I'm going to do next is combine all of our constant values. I'm going to underline them for you. We have 1,000 right here, we have 200 right here, negative 250 there, positive 360, and then negative 100. If you combine all of those numbers together, you should get 1,210. So $1,500 is equal to $1,210. And then we have all of our terms with I to deal with. Okay, so we have plus 1,000I plus 200 times 5 is 1,000. So we have 1,000 divided by 6 times I. But if you're to write that out, 1,000 divided by 6, you can reduce the numerator and denominator by a factor of 2. Both of them are divisible by 2. So 1,000 divided by 2 is 500, and 6 divided by 2 is 3. So really we have plus 500 divided by 3 times I, or 500 thirds times I. Then let's move on to this term. We have negative 250I times 2 thirds. 250 times 2 is 500, so we have minus 500 divided by 3 times I. And would you look at that, that's kind of nice. These two terms are going to cancel out. We have positive 500 thirds times I and negative 500 thirds times I. So really, we can just cross those out right now. But moving on to our next term here, we have 360 times I times 5/12. 360 times 5 is 1,800. And so you'd have 1,800 divided by 12. But 1,800 is divisible by 12. It's 150. So what we have here is plus 150 times I. And then, of course, we still have this negative 25I to account for. Okay, so now what I want to do is combine all of our like terms that have I, and then I'm going to subtract this constant value from both sides of the equation. So if we subtract that from 1,500, we will get 290, and that will be equal to 1,000I plus 150I minus 25I. 150 minus 25 is 125, so if we add that to 1,000, you get 1,125 times I. All right, and now solving for the dollar-weighted rate of return, which is this right here, is as simple as dividing both sides by 1,125. And if you do that, you will find that the dollar-weighted rate of return is equal to 0.2578 and some more decimals. In fact, I think it's 0.257 repeating, but I'm just going to round it off there, which would be 25.78%. That is the dollar-weighted rate of return for this investment account. All right, so that's half the problem. We just found the dollar-weighted rate of return. Now let's work on finding the time-weighted rate of return. To find the time-weighted rate of return, we need to use a different formula, and we're going to be using all of the given values in our table that we've also labeled on our timeline. Here's our setup. To find the time-weighted rate of return, we want to take the first reported balance, which is $1,150. I'll write that, and divide it by the initial balance of the account, which is $1,000. Okay, you always start with the first reported balance, not the balance at the beginning of the year, but the first one reported after that, and divide it by the original account balance. Then you want to multiply by a fraction where the numerator is the next reported balance, which is 1,400. So we have 1,400, and then you are dividing by the previous reported balance plus or minus any cash flows. In this case, we want to add 200. So we have 1,150 plus 200, which is 1,350. All right, so I'll write 1,350. Then we want to multiply by the next reported balance, 1,200, so I'll write that in, divided by the previous reported balance, plus or minus any cash flows. So we have 1,400 minus 250, that would be 1,150. So we have 1,150, and then we multiply by the next reported balance, which is 1,700, and divide that by the previous reported balance, plus or minus any cash flows. So we will be multiplying by 1,700 divided by 1,200 plus 360, which is 1,560. So we'll have 1,560. And then finally we multiply by the last reported balance, or the balance at the end of the year, divided by that previous reported balance, plus or minus any cash flows. In this case, we are subtracting 100. So we have 1,500 as our final balance divided by 1700 minus 100, which is 1600. Okay, so we'll multiply all of that together and then subtract 1, and that will give us the time-weighted rate of return. And so if you do perform this calculation, you plug all of it into your calculator, you should get that the time-weighted rate of return is about 0.2714, and some more decimals. I rounded off to 4 decimal places, which would also be 27.14%. Okay, that is the time-weighted rate of return for Mia's investment account. And so with that, we have now calculated both the DRR and the TRR for this account, and so we are done with this 4th review problem. Let's move on to the next one. All right, so for our 5th review problem, we have Richard needs $21,000 to purchase a new car. Bank A agrees to lend him $21,000 now in exchange for loan payments of $1,125 at the end of each quarter for the next 6 years. Bank B also agrees to lend Richard $21,000, but the loan payments would be $330 at the end of every month for the next 6 years. Using the internal rate of return as the measure, which bank should Richard choose for his car loan? Okay, so if you want to try this problem out for yourself, now is the time to pause the video. But if you're ready to see me work through the answer, then feel free to let the video play on, because now I'm going to work through it. And hopefully it's clear that we are working with the internal rate of return in this problem. This is a little bit different than our problem from earlier, where we were just trying to calculate the internal rate of return, and that was it. We're still going to end up doing that in this problem, but there's a little bit more to it. We're not just calculating an internal rate of return. We're going to be using it to help Richard make a decision on which bank he should get his car loan from. And we'll talk about how we'll make that decision later on. For now, let's just focus on what our calculations are. Because what we're going to have to do here is determine which bank's loan has the more attractive internal rate of return for Richard, right? That's how Richard is going to make his decision, because we were told in the problem to use the internal rate of return as the measure, okay? And again, we're going to talk about how exactly we'll do that once we calculate these internal rates of return. So let's talk about how we're going to do that. Let's start by taking a look at Bank A's loan. They agreed to lend Richard to $21,000 starting today, but it will be in exchange for loan payments of $1,125 at the end of each quarter for the next 6 years. All right, so that's 4 payments per year, 1 every quarter for 6 years. So that would be a total of 24 payments, right? So for Bank A, here's what our timeline looks like. This will be time 0, and then Richard is going to have to make a total of 24 payments for that loan. So this will be time equals 24, right? N is equal to 4 payments per year for 6 years, which is 24. All right, so then we'll have time 1, time 2, and then I'm going to skip ahead to time 22 and time 23 up to time 24. Okay, because the payments are going to remain the same throughout those 24 quarters. The important thing to notice is that there are 24 of those payments. Okay, so if we're looking at the inflows and outflows for this scenario, there's an initial investment of $21,000 at time 0, right? That is an outflow of money. We have minus $21,000 at time 0, and then every payment after that will be an inflow, a positive payment of $1,125. So we have 1125 there, 1125 there, and that continues all the way up till time 24. So we have 1125, 1125, and 1125. So if we were going to set up our equation where we have 0 equal to the net present value, this is what it would look like. We would have 0 is equal to that initial investment of negative 21,000 plus the present value of all of these payments, right? This negative $21,000 is already valued at time 0, but now we want to value all of these payments at time 0, which we could do by using an annuity immediate notation, right? We'd have 1125 times A, 24 bracket, the interest rate, which would that be our internal rate of return? Well, it's a form of the internal rate of return, but it's going to be a quarterly rate, because these payments are being made quarterly and our number of periods is measured in quarters. So this interest rate that we would have to use for this calculation would be a quarterly effective interest rate. And so when we go to actually compare our internal rates of return, we're probably going to want to convert that to an annual rate, but we'll worry about that later. For now, just note that this will be a quarterly rate, J sub 4, that we would want to find. Okay, so that's our setup for Bank A. We'll come back to finding that rate in a little bit. Let's move on to the setup for Bank B. Bank B also agrees to lend $21,000, but the payments are different. Instead of quarterly payments of $1,125 for 6 years, there will be monthly payments of $330 for the next 6 years. All right, so here's what we have for Bank B. The total number of payments will be 12 times 6 because the payments are being made monthly. There's 12 months in a year, and Richard would have to do it for 6 years. So we have a total of 6 years to multiply that by, and 12 times 6 is 72. So there would be a total of 72 payments of those $330. All right, so here's a timeline for Bank B. This is time equals 0, and this would be time equals 72. So we have time equals 1, time equals 2. We'll skip ahead to time equals 70 and time equals 71. There is an initial investment of negative 21,000, and then after that, we have payments of $330 every month for 72 months. Okay, and it is important to note that those are taking place at the end of every month, and so that's why the first one is at time 1 and not at time 0. Okay, just like how these payments were being made at the end of each quarter, so the first one was at time 1, not time 0. All right, so now our equation for calculating the internal rate of return would look like this. We'll have 0 equal to the net present value of all the cash flows in this scenario. So we need to value all of these cash flows at time 0. So we already have one of them at time 0. That's negative 21,000. But then we need to add that to all of these other payments valued at time 0, which once again we can do using an annuity immediate notation. We'll have $330 times A 72 bracket J sub 12, right? These $330 payments are monthly payments. They're being made for 72 months. So the interest rate that would be used for that calculation for an annuity immediate would need to be a monthly rate. Okay, so that's why it's J sub 12. So this is a setup for Bank A, and this is a setup for Bank B. Now what we want to do is calculate these interest rates. Now, they're not going to be annual effective rates. We will need to convert them to annual effective rates, and those will be the internal rates of return that we end up comparing to determine which bank Richard should choose. Okay, now we'll worry about that in a little bit. For now, we need to actually solve for J sub 4 and J sub 12. And this is where doing things by hand might get a little bit tricky. I typically like to show you the algebra in these videos, but I am going to have to pull out a financial calculator in this case, because solving for an unknown interest rate in an annuity formula can be quite tricky. So it doesn't make sense for us to do that here. Let's just make use of a calculator that can do it for us. Note that in either case, $21,000 is going to be the present value of the payments for the annuity, right? So if you add $21,000 to both sides of the equation, this is what you get. And you could do the same thing down here. You'd have 21,000 is equal to 330 A 72 bracket J sub 12. All right, and before I pull out the financial calculator, I just want to make a quick note here. You might have thought that earlier we should have made the $21,000 positive and then all of these payments negative. But as you'll see with this equation, that really wouldn't have mattered for what we're going to do here to find these interest rates. Because if this was positive and this was negative, and you added this to both sides of the equation, then both sides would be positive. So it's no different than what I have right here. Okay, so if you flip these payments to being negative and this initial investment to being positive, you're still going to end up with the same equation for calculating this interest rate. Okay, but at this point, in order to solve for these interest rates, we do need to pull out our financial calculator. So that's what I'm going to do now. To solve for these unknown interest rates, we will need to make use of the time value money buttons on the financial calculator. That would be these white buttons right here, the N, I/Y, present value, payment, and future value buttons. But before you do any of that, be sure to clear out those values. You can do that by hitting the second button and then the future value button, which above it says clear TVM. Okay, so now we're good to go. If you don't clear that out, it may affect your answer, and you don't want that. Okay, but in this case, for this equation right here, for Bank A, $21,000 is our present value. So I'm going to punch in 21,000, and then I'm going to make that the present value by hitting present value. Then our payments are $1,125. Now, when you put in both the present value and the payment amount, one of them must be negative in the calculator, just like how one of them had to be negative in this net present value equation. That's sort of the idea here. So I'm going to make the payments negative, even though that's the opposite of what I did in the equation here. As I just got done explaining, it doesn't matter as long as one of them's negative, one of them's positive. You're fine. So I'm going to punch in 1,125, make it negative, and then make that the payment amount. Then we have 24 of those payments. So I'll punch in 24, make that N, and then we don't know what the interest rate is, so that's what we're going to compute. So we're going to hit compute and then I/Y for the interest rate, and that will give us an interest rate of 2.12% if you round off to 2 decimal places. Now you might have noticed the calculator did take like half a second to calculate that, and that's because it is sort of a complicated calculation, which is why I decided not to do it by hand here. Okay, if you're solving for an unknown interest rate in an annuity formula, your best bet is to use your calculator. All right, but by using the calculator, we have now found that the quarterly effective interest rate for Bank A, or J sub 4, is equal to 2.12%. And try to write down as many decimals as possible when you're doing this for your own work, because we are going to have to convert this interest rate to an annual effective rate in order to compare it to the other interest rate. But we'll come back to that. For now, let's calculate what this interest rate would be, J sub 12, the monthly effective interest rate that would be used for the loan from Bank B. So we need to do another TVM calculation here. That's going to save us a lot of time. So what I'm going to do is clear out my work here and then clear out the time value money buttons again. So hit second future value. And now let's start over. We have a present value of 21,000. So do 21,000. Make that the present value. Our payments this time are $330, and I am going to make them negative because one of those two things, either the present value or the payments, need to be negative in the calculator in order for this calculation to work. So we have 330, make it negative, make that the payment amount. And then we have 72 of those monthly payments. So 72 is N. And then we want to compute the interest rate once again. So we'll hit compute I/Y, and there it is. This time it's 0.35% if you round off to 2 decimal places. So that's our monthly interest rate. Okay? So we have now found that J sub 12 is equal to 0.35%. Okay? So now we're good to go. We were able to use our financial calculator to help us save some time here, because like I've already said, trying to find those interest rates by hand would not have been very fun. Okay, so now we have found the internal rates of return for each loan from each bank, but they are in terms of their own period type. So for Bank A, that would be quarters. We have a quarterly effective interest rate or an internal rate of return that is quarterly. And for Bank B, we have a monthly effective interest rate or an internal rate of return that occurs monthly. And so in order to compare them to decide which loan Richard should choose, we need them to have the same frequency. So let's convert both of them to annual effective interest rates, and then we can compare them. And so let's do that. I'll start by converting J sub 4 to an annual effective interest rate. We'll have that I is equal to 1 plus J sub 4, which is 2.12%. So we have 0.0212 to the power of 4, the number of times that rate would happen in a year. So a quarterly rate would occur 4 times in a year. And then you subtract 1. And then let's set up this conversion as well. We have a monthly effective interest rate. So we will have that I is equal to 1 plus 0.0035 to the power of 12 minus 1, right? This is a monthly effective interest rate. This is that rate as a decimal, and it would occur 12 times in a year. So that's why the power is 12. Okay, so if you were to do these two calculations, you should find that the interest rate for Bank A is equal to 0.0874 and some more decimals, or 8.74%. And then the annual rate for Bank B, or its internal rate of return, that would be equal to 0.0423 or 4.23%. Okay, so those are the two interest rates or the two internal rates of return in this problem. This is the internal rate of return for Bank A's loan, and this is the internal rate of return for Bank B's loan. We have 8.74% versus 4.23%. So now the question is, which one do we want? Which one is better, and which bank's loan should Richard choose? Well, if we think about it logically here, Richard probably wants to pay the least amount of interest on his loan as possible, right? Whenever you take out a loan, the worst part is the interest that you have to pay off. So the less interest you have to pay, the better, which means that Richard would want the smaller interest rate, right? He would want a smaller rate rather than a bigger one because a smaller rate is going to generate less interest than the bigger interest rate, okay? So from our two options here, does Richard want 8.74% interest or does he want 4.23% interest? I think he wants 4.23, right? It's a lot smaller of an interest rate, so Richard probably wants that because then he'll pay less interest in the long run. Okay, so that's our final answer here. Richard should choose Bank B. Okay, I'll write that right here. Richard should choose Bank B. That's the bank whose loan he should take. All right, and if you want to provide a reason, you can say that Bank B has a lower internal rate of return. Okay, and so with that, that is the end of this fifth review problem. And so let's take a look at the next one. Okay, so for our sixth review problem, we have Mark is considering purchasing one of two assets. Asset 1 has payments of $6,000 at the end of year 1, $13,000 at the end of year 3, and $18,000 at the end of year 5. The price of Asset 1 today is $31,000. Asset 2 has payments of $15,000 at the end of year 4, $21,000 at the end of year 5, and the price of Asset 2 3 years from today is $33,000. Given the yield curve below, what is the 3-year forward rate? Okay, so if you want to challenge yourself, now is the time to pause the video and try this problem out for yourself first, but once you're ready to see how I go about solving this, feel free to let the video play and see the solution. All right, but in this problem, we are working with spot rates and forward rates. We've been given this yield curve where we have different term lengths and their respective spot rates, although we don't know all of them. We do know 3 of them, but 2 of them are unknown. That might cause us some issues later on in this problem that we will have to deal with. But for now, it's good to identify that, yes, we're working with spot rates, and we want to find some forward rate that we don't know. Now, in order to do that, we are going to have to make use of this other information that we've been given about Mark, who is considering purchasing one of 2 different assets, Asset 1 or Asset 2. And so to really get an idea of what we're working with here, I think we should draw a timeline. Let's make sense of these 2 different assets, when the different cash flows are coming in, and where their prices are valued. Okay, so here's my timeline. This right here will be time equals 0. And I think the last moment in time that we need to include is time 5, because we have 2 cash flows for these 2 different assets that would be received at time 5. And also, we've only been given spot rates up to a term of 5 years, so we should probably only work with 5 years in our timeline here. So the end of our timeline is t equals 5, and then in between there we have time 1, 2, 3, and 4. Now, let's start with Asset 1. I'm going to put Asset 1's cash flows right here in this row below the timeline. Asset 1 has payments of $6,000 at the end of year 1, so that would be right here at time equals 1. We have $6,000, and then $13,000 at the end of year 3, so that would be right here. So we have $13,000, and then $18,000 at the end of year 5. So those are the cash flows that are received from Asset 1, but the price of Asset 1 today, so that's its value at time 0, is $31,000. Okay, so the price or the present value is $31,000. Okay, now let's move on to Asset 2. Asset 2 also has payments or cash flows. Asset 2 has payments of $15,000 at the end of year 4 and $21,000 at the end of year 5. All right, so this will be where I put the cash flows for Asset 2. I'll put them in this row below the timeline. We have a payment of $15,000 at the end of year 4 and $21,000 at the end of year 5. Okay, and then we also know that the price of asset 2 3 years from today is $33,000. Okay, so that's telling us that the price of the present value at time equals 3 is 33,000. So in this case, the present value is 33,000 and it's valued at time 3, not time 0. Okay, so this is the information that we have been given in this problem. This is what we know, and we need to use this information to find a 3-year forward rate. And what is that? Well, remember the phrasing here. A 3-year forward rate is telling us that we want a forward rate that starts at year 3 and ends at year 4. All right, another way that you could view it is a 1-year forward rate deferred 3 years. Okay, the default is a forward rate takes place for a 1-year period unless you were told otherwise. In this case, all the information we have is that this is a 3-year forward rate, so we can assume that that is a 1-year forward rate that begins at time 3. Okay, so what we're looking for here is f sub 3 comma 4. That's the forward rate we want to find. And so how are we going to go about finding that? Well, it's not initially clear, but something that we should probably do is set up some equations using these cash flows that we've been given and their prices or present values, right? We wouldn't be given that information if we weren't expected to use it. So let's just set up some equations and see what we can learn from setting up those equations. And let's start with asset 1. We know that the price of asset 1, or its present value, is $31,000, so that's going to be equal to these 3 cash flows valued at time 0. So let's do that. Let's set that up. For asset 1, we have $31,000 is equal to these 3 cash flows valued at time 0. Let's start with 6,000. We'll have 6,000, but it needs to be brought back 1 year. So we're going to be multiplying by present value factor to the first power, but what interest rate would we be using? Well, we would be using a spot rate for a 1-year term, right? This spot rate right here, 4%, that is going to be used for a term length of 1 year starting from time equals 0. That is where this spot rate would take place. So we are going to use S sub 1 for that present value factor. Now let's move on to our next cash flow. We have 13,000 at time 3, but that needs to be brought back 3 periods. So we have 13,000 times V cubed, a present value factor cubed. But now what interest rate would we use for that present value factor? Well, we can't use S sub 1 like we just did right here. We need to use a different spot rate, in particular a spot rate for a 3-year term length, right? We have a 3-year term from time 0 to time 3, so we would want to use S sub 3. Now, we don't know what that rate is currently. It's unknown. We don't know what it is like we do for S sub 1, but we do know that that is the rate that would need to be used for that present value factor. Okay, so S sub 3 would be used for that present value factor. Now, we need to add that to our last cash flow, but valued at time 0. We have $18,000 at time 5, needs to be brought back 5 years. So we'll have 18,000 times a present value factor to the power of 5, and the interest rate that we would use would be a spot rate for a 5-year term length, right? We need to bring the $18,000 back 1, 2, 3, 4, 5 years, which is a term length of 5 years from time equals 0. So we would want to use this spot rate right here. Okay, so we would be using S sub 5. Okay, and let me just label that on the timeline real quick. From time 0 to time 5, that would be for S sub 5. So I'll write that here, S sub 5. This other one was for S sub 1, and then S sub 3 would be for a 3-year term length. So that would be this right here. Okay, S sub 3. Now, this setup is done. This is good for asset 1. However, since we do know what this spot rate is and this spot rate is, I'm going to actually write in what those decimals would be for those rates. So S sub 1 is 4%, so that's just 0.04. And then for S sub 5, we have 5.25%, so that will look like this. We have 0.0525 as that spot rate. All right, and now you can see in this equation, there's only one unknown value, and that is this spot rate, S sub 3. So we could probably solve for it if we need to. In fact, we will probably have to do that later on. But before we do that, let's just set up an equation for asset 2, like we did for asset 1. And for asset 2, the price or the present value is not valued at time 0, it's valued at time 3. So things get a little bit tricky here. Instead of valuing everything at time 0, we need to value everything at time 3 so that they're equal to each other. Because if we're going to write 33,000 is equal to those other cash flows, those two cash flows also need to be valued at the time where that present value is valued, which in this case is time 3. So let's take a look at the first cash flow here. We have $15,000. We're going to have 15,000, but it needs to be brought back one period. So we would need to multiply it by V to the first power. But what would the interest rate be? Would it be a spot rate for a 1-year period? No. Because S sub 1, this spot rate is assuming that you were starting at time 0 and then accumulating for 1 year. That's not the case. We're starting at time 3 and ending at time 4. Or I guess more accurately, we're going from time 4 to time 3, but regardless, we would want the interest rate that would take place for that period, which would be a forward rate from time 3 to time 4, the exact forward rate we're trying to find. All right, so the present value factor is going to use the interest rate of F sub 3, 4. Now let's add that to the present value of this cash flow of $21,000. We need to bring that back to time 3 as well. And so that is 2 years in the past. So we will add 21,000 times V squared because we need to bring it back 2 years. But what interest rate will we use for that? Well, we would need to use an interest rate that takes place between time 3 and time 5. And so given our yield curve, we're working with spot rates and forward rates, we can't just use any old interest rate. We need to use a forward rate that takes place from time 3 to time 5. Okay, you can't use S sub 2 or a spot rate for a 2-year term because that is assuming that you are starting at time 0, which we are not in this case. We are starting at time 3, so we need a forward rate from time 3 to time 5. Okay, spot rates always start at time 0, but if you start anywhere else, you're going to be working with a forward rate. So the forward rate we need in this case is a forward rate from time 3 to time 5. It spans a 2-year period, which is kind of tricky, but it's nothing that we can't do. All right, now we don't know what either of those forward rates are. However, we could find them if we knew the right spot rates. In order to find a forward rate from year 3 to year 4, we would need to know the spot rate for year 3 and the spot rate for year 4. And unfortunately, we don't know either of those. And to find the forward rate from year 3 to year 5, we would need to know the spot rates for a 3-year term and a 5-year term. And as of right now, we only know one of those. We know the spot rate S sub 5, but we don't know S sub 3. But remember, we can actually solve for it in this first equation here. That's the only thing we don't know in this equation for asset 1. So we should be able to find that. We can find S sub 3. Then we can use S sub 3 and S sub 5 to find this forward rate. And then we'll know everything in this equation except for this forward rate, so we will be able to solve for it. That will get us to our final answer and the solution to this problem. Okay, so kind of complicated. The solution is not super simple, but we can at least see how we're going to get there. Now we just have to do the work. So let's get started here. The first thing that we should do is solve for S sub 3. And let's do that right here. We'll have 31,000 is equal to 6,000 divided by 1.04, right? That is just this present value factor. It would be 1 divided by 1 plus that spot rate. So we're multiplying 6,000 by 1 divided by 1.04. And in the same way, for these two terms, we would have this cash flow multiplied by 1 divided by 1 plus this spot rate to the power of 3. And we'd have 18,000 times 1 divided by 1 plus this spot rate to the power of 5. So that will look like this. We have plus 13,000 divided by 1 plus S sub 3 cubed plus 18,000 divided by 1.0525 to the power of 5. Okay? Now, if you plug 6,000 divided by 1.04 in your calculator, you will get this. We're going to have 31,000 is equal to $5,769 and about 23 cents. That will be added to that 13,000 divided by 1 plus S sub 3 cubed. And then if you plug this into your calculator, we will have $13,936 and about 77 cents. And so if you subtract this value and this value from both sides of the equation, in other words, we're subtracting them from 31,000, we will have $11,294, and that will be equal to that 13,000 divided by 1 plus S sub 3 cubed. Okay, so now, in order to solve for that spot rate, what I'm going to do is divide both sides by 13,000. And so if we do that, we will have 11,294 divided by 13,000 is equal to 1 divided by 1 plus S sub 3 cubed. And now, if we take the reciprocal of both sides of the equation, or flip the numerator and denominator on both sides, I'll do that up here. We'll have 13,000 divided by 11,294, and that will be equal to 1 plus S sub 3 cubed. And now you can take the cubed root of both sides and subtract 1 to solve for S sub 3. If you do that, you should find that the spot rate for a 3-year term length is equal to about 0.048. Okay? And I'm just rounding it off there. It's about 4.8%. And so that's good. Now we know what the spot rate for a 3-year term length is. We know it's 4.8%, which means we can now use that to find this forward rate from year 3 to year 5. Once we know that forward rate, then we know everything in this equation except for this forward rate, which is the forward rate we want to solve for. Okay, so let's work on finding this forward rate from year 3 to year 5 next. Remember that a forward rate from year 3 to year 5 would take place for this period right here. So the way we set up an equation to solve for it is to say that accumulating from time 0 to time 5 using a 5-year spot rate would be the same as accumulating using a spot rate from time 0 to time 3, or S sub 3, and then accumulating for an additional 2 years using that forward rate, right? So that would look like this. We're going to have 1 plus S sub 5 to the power 5 is equal to 1 plus S sub 3 cubed times 1 plus F sub 3 comma 5 squared. Okay, once again, what this is saying is that if you took an investment of $1 and accumulated it for 5 years using S sub 5, that would take it from time 0 to time 5, that would be the same as taking that $1 and accumulating it for 3 years from time 0 to time 3 using S sub 3, and then for an additional 2 years to time 5 using this forward rate from year 3 to year 5. Okay, so plugging in what we know, we'll have 1.0525 to the 5th power is equal to 1.048 cubed. And by the way, there are some more decimals after 0.048 for that spot rate. Try to include some of those if you can when you do this calculation. That will get you the most accurate answer for the forward rate. But that would be multiplied by 1 plus F sub 3 comma 5 squared. All right, now we need to solve for this forward rate. So we want to divide both sides by this accumulation factor. So we have 1.0525 to the 5th power divided by 1.048 cubed. And that will be equal to 1 plus F sub 3 comma 5 squared. But if we want to solve for that forward rate, we need to take the square root of both sides of the equation and then subtract 1. If you do that, you will find that F sub 3 comma 5 is equal, or the forward rate from year 3 to year 5 is equal to 0.05927 and some more decimals. Okay, so now we know the forward rate from year 3 to year 5, which we can use in this present value factor in this equation, which means that the only thing we don't know is this forward rate from year 3 to year 4, which we could solve for, and that will be the solution to our problem. That's the forward rate we wanted to find. Okay, so now let's work on that next. I put our forward rate up here that we just found. If we work with this equation here for asset 2, let's do that right here. We will have 33,000 is equal to 15,000 divided by 1 plus this interest rate, right? This present value factor would be 1 divided by 1 plus this forward rate. So we just have 1 plus F sub 3 comma 4, and then we're adding that to 21,000 divided by 1 plus this forward rate squared, right? This present value factor would be 1 divided by 1 plus this forward rate squared, so we're just multiplying it by 21,000. So in the denominator, we have 1 plus F sub 3 comma 5 squared. All right, now we know what F sub 3 comma 5 is. It's right here. So let me just rewrite that. to be what it would be with that actual forward rate, we'll have 1.05927 squared. If you do this in your calculator, you should get about $18,715 and about 62 cents. And so you have 33,000 equal to this right here. I'm just going to represent that like this. I'm going to put a little square there. This would be right here. So if you subtract this amount from both sides of the equation, meaning you subtract 18,715 from 33,000, this is the equation you'll end up with. You'll have $14,284 and about 38 cents is equal to 15,000 divided by 1 plus f sub 3 comma 4. Okay, then dividing both sides of the equation by 15,000 will take us to this. We'll have 14,284.38 divided by 15,000. That is equal to 1 divided by 1 plus f sub 3 comma 4. Remember that we are trying to solve for that forward rate. So now if we take the reciprocal of both sides of the equation, we have 15,000 divided by 14,284.38, and that's equal to 1 plus f sub 3 comma 4. And now if you calculate this in your calculator, subtract 1, that will solve for the forward rate that we're trying to find. And if you do that, you should get that f sub 3 comma 4, or the forward rate from year 3 to year 4, is equal to 0.0501 or 5.01%. Okay, that is the final answer to this problem. That is the 3-year forward rate, or the forward rate from year 3 to year 4. Another way that you might hear that is a 1-year forward rate deferred 3 years. But regardless, that is the final answer. It's 5.01%. And so it was a lot of work to get there, but we were able to find the forward rate in the end. All right, and so with that, that is it for this 6th review problem. It's also the last review problem for this video. However, I do have 4 more available on my membership site, JK Math Plus, that you could get access to if you become a member. Now, those 4 example problems are not the only things available on my membership site. There's a lot more on there. There's a lot of other review problems for other units, as well as some other example problems for financial mathematics, and all the other courses I cover on my channel as well. And so if you do want to get some more practice, you want to solve some more problems and see how I solve them, feel free to look into joining my membership site. You can learn more by heading on over to my website at jkmathematics.com/plus. Okay, so feel free to check that out if you're interested, but if not, that's fine too. If you have any questions about any of the problems or anything that I covered in this video, please let me know in the comments. But if you don't have any questions, then that is all I had for this Unit 4 review video, and so I will see you next time.